Okay, thank you very much. So the talk I'm going to give now is really a talk by Joanna Morgan, but she couldn't join us at this session, so I'm going to give the talk. I'm going to talk to you about the use of full waveform inversion to tackle various scientific problems. So we've heard about the applications of FWI to solve industrial problems, and that's the major use of FWI. But it also has great potential to solve a much wider range of problems, and it's that range of problems and what we might do with it in the future that I'm going to talk about for the next few minutes. So to set the scene, there are lots of potential scientific targets that FWI might address. So some of them are listed here, some of them are shown as pictures. So the sorts of things we're interested in are understanding impact craters, understanding subduction zones, understanding active faults on a whole variety of scales, understanding plate boundaries like mid-ocean ridges, understanding the details of active volcanoes, looking at large-scale structures across continental margins, looking in the deep crust, looking at smaller things like the interiors of ice sheets. All those sorts of things are scientific targets that we can improve the imaging of, that we can learn more about, that we can get the physical property models by using FWI. Of course, to do that, we need to collect the right sort of data that we can apply FWI sensibly to, and that leads us to a number of challenges. So many of the scientific targets that we'd like to look at have some or all of these sorts of problems. They're often quite deep. Often the things we want to see scientifically are a lot deeper than the things we would like to see in petroleum exploration. Not always, but generally they're deeper. Typically that means we need longer offsets, and in petroleum perhaps long offsets are 10, 15, 20 kilometers. In the context that I'm going to talk about, long offsets are often 100 kilometers, sometimes they're 200 kilometers. And if you're trying to do an experiment, a multi-azimuth experiment with offsets to 100 or 200 kilometers, that gets extremely challenging. Our velocities are often a lot higher, which means the wavelengths are lower for a given frequency, and that can also be an issue. But probably the biggest issue for us is this one, that our data for most scientific targets is extremely sparse, much more sparse than you would ever dream of using in the petroleum industry. And why is that? The reason for that is because scientists are poor relative to oil companies that are relatively rich. So oil companies can afford to collect vast amounts of data, and most scientific endeavors cannot afford to collect those large volumes of data. So we're dealing with quite sparse data, and that's one of the things that I'll come back with. I'll show you its consequences, but one of the things that I'm going to come back with at the end of the talk. A couple of other things. Our locations, often the locations that we're going to want to study with scientific FWI, they're often remote, by which I mean they're often remote from the places that people are doing petroleum exploration. So if we want to take the same equipment, the same ships if we want to use those from the petroleum industry, they're often a long way away from the places that those ships are typically located. So that's an issue. And then very often we end up with some sort of suboptimal acquisition. The data's sparse, we can't use the full offsets that we would really like, we can't use the full azimuths that we would like. So lots of things are suboptimal about the sort of data that we can often collect for scientific FWI. So a whole series of challenges, which you'll see. The outline of the talk, I'm going to talk about talk briefly about 5 different applications of FWI. The first 3 are studies that have happened. 2 of them are studies on field data. One of them is a study on synthetic data. And then 2 experiments that will happen in the next year or 2 that are specific acquisitions designed to support FWI interpretations. And then at the end, I'll make a suggestion as to how what Brazil might do to play in this area. And there's something very, very special and genuinely world-leading that Brazil could contribute to this activity. So I'll come to that at the end. So I'll start by looking at field data across the Chicxulub impact crater. So the Chicxulub impact crater is a big buried impact crater in Mexico. It's the impact crater that wiped out the dinosaurs. It's the impact crater that happened, or the impact event that happened at the end of the Cretaceous. So at the end of the Cretaceous, 65 million years ago, life looked something like this. There were large reptiles on land. There were large reptiles in the air and the sea. There were ammonites and a whole variety of other life forms. All of those disappeared. So when this impact occurred at the end of the Cretaceous, they all vanished. The largest animal that was left on land after this impact weighed about 10 kilograms, the size of a medium-sized dog. Everything larger than that disappeared on land. So the impact basically takes us to here. This is before the impact. This is after the impact. This is basically one of our ancestors. This is a small mammal. It was a shrew-like mammal. They survived this event. Everything else disappeared. And that basically allowed evolution to proceed. And we go from there basically to here. So this is how evolution has moved. So I debated which way around the arrows were, but I think I got them the right way around. So Felix would not be here today if it were not for this impact, and none of us would have been here. So these little creatures had been around for a long time. They'd not been very successful. They hadn't been doing very much. And it was the fact that everything else disappeared from land that basically allowed the mammals to grow, to appear, and to evolve, to turn into us today. So the Chicxulub impact was a very, very important event for our species, for mammals in general, for the history of life on the planet and so on. So we'd like to understand it. So we have collected seismic data across the Chicxulub impact. So here's a bit of that seismic data. Here is something that's loosely analogous to what the Chicxulub impact would look like on the moon. So this is an impact crater on the moon. And in this particular crater, you can see it's got a flat floor, and then it has this ring of hills around here, this topographic ring, which we call a peak ring. And craters on most silicate objects in the solar system of about the right size have this structure. They have this peak ring sitting within them. And we don't really know what causes peak rings. We don't really know why impact craters look like that. And if you look at the seismic data across the Chicxulub impact, and there's a scale on here, this is 50 kilometers. So this is a line, not quite through the middle, but it's sort of obliquely through the middle of the impact crater in Mexico. And you can see it's got a peak ring. It's this feature here, and then the middle of the crater's here, and then that's the other side of the peak ring there. So we're looking at a slice sort of equivalent to a line about like that. It doesn't quite go through the middle, but there's the buried topographic peak ring. There's the buried topographic peak ring. This is the edge of the crater here, the edge of the crater here equivalent to this crater edge. And of course on Earth is an active planet, so the basin here is all filled with sediments. On the moon is not active. It doesn't really have any sort of active sedimentation, so if you make a hole, it stays there for a very long time. On the Earth, if you make a hole, it inevitably fills with sediment. So we can see this buried impact crater. We'd like to understand a little bit more about the process that made that and the process that wiped out the dinosaurs and led to our own evolution. So there's various ways we can do that. So one way we can do that is to model it. So this is a fairly simple axisymmetric model. So this is the Earth's surface. Here is this object arriving, this meteorite arriving, about to hit the Earth. It's traveling downwards in this model at about 30 kilometers a second, 30 kilometers a second. So that's extremely fast. That's much faster than the seismic velocity in this material. So it's a hypersonic impact. It's about 12 kilometers across, or thereabouts. And on the picture here, the base of the crust is here. The lines just represent particular depths in the original model, so you could think of those as a sort of artificial stratigraphy that you can watch how it evolves as this crater happens. And on this side, the colors are temperatures, so it's cold at the top, and it gets hotter as we go down into the Earth. And the bolide itself, the object itself, is pretty cold. So it's moving extremely fast, and this is just at the moment that it's hit the surface. And then if we run that, assuming I can make that work, It looks like this. So this is the impact event, and that's how it evolves. That takes about 2 minutes or so to do that. Let's just see if I can manage to run that again. If I can figure out how to use a Mac. So it's about to hit. It hits. It does that. Let me just stop it there. So, and see if I can show you the scale. So this is 0. This is 40 kilometers up in the air. This is 40 kilometers down. So this object here is sticking out the top of the atmosphere. The atmosphere is only about 10 kilometers high. I mean, it gradually disappears, but it's the half height of the atmosphere is about 10 kilometers. So this is huge. This horizontal scale here, this is minus 100 to plus 100 kilometers. So this is about a whole 100 kilometers or so across, and it's about 30 kilometers deep. And you can see, well, it pushes the base of the crust out of the way. It doesn't penetrate it. You'll see as we carry on, although it goes deep, it pushes it out and then it flows back again. And you can see here it's beginning, this is going out, and this is still built, but in the middle here, this is starting to come back up again. So gravity on the Earth really doesn't like holes that are 30 kilometers deep. Rocks are not strong enough to support that. So as soon as you make a deep hole, the first thing that happens is that essentially the weight of the stuff on the side will push the middle back up again. So this is attempting to come down and push this up. This whole thing is not gravitationally stable, so the middle will come flying up, basically driven by gravity. It's not elastic or anything. It's not an elastic rebound. It's simply a gravitational effect. So this whole video lasts, I think it lasts about 90 seconds or 2 minutes, something like that. So this is happening very, very quickly. Let's see if I can just make that. So you can watch it carry on. So this peak is rising up. So this peak now is much higher than the Himalayas. So this is 20 kilometers up in the air. This mountain, it's not really a mountain, but this pile of rock now sticks out of the atmosphere. And you can see things are flowing. You can see the edges are beginning to collapse. And if it continues, it looks. So the meteorite, much of it will vaporize. So there's a big plume of vapor, looks like the sort of plume that you would get from a very, very, very large nuclear explosion. So you get this plume that rises like a mushroom cloud, except it rises to about 2,000 kilometers high. So it's clearly much, much bigger than any nuclear weapon we've ever fired. Most of the plume goes in that. A little bit of it is melted. So most of it's vaporized. I think about 98% is vaporized. About 2% is melted and remains basically in this region, and a very small percentage, there is a physical process which allows little bits to spill off basically the meteorite. You can get very small solid bits that are not very shocked and not very heated that survive. So there is one fragment, supposed to be one fragment, a few microns across of this meteorite found in a borehole in the deep ocean. That's supposed to be from this meteorite. It has the right age and some other characteristics that are right, but it's not completely clear that it is. The material that vaporizes, most of that goes into orbit around the Earth and eventually falls back on the Earth, and you find it everywhere. So if you go to rocks anywhere for the right age, you find a thin layer a few millimeters deep with this material in it. So there's none in the UK, but so the nearest there is Denmark. Italy's the nearest place to the UK. Brazil, I'm not sure where it would be in Brazil, but there certainly are rocks of the right age, so there should be deposits in Brazil. The classic place is across the middle of the US, because this is quite close to the US, and a lot of the fallout fell onto the southern US, so you can find it quite easily there. So we'd like to understand more about that. So what can we do? We can get our seismic data, and we can try to do full waveform inversion on the seismic data, try to relate the FWI to various rock types. So this rather complicated composite image, it shows some reflection data. It shows a full waveform inversion image. This is the peak ring. This is that higher resolution than we saw before. These are melt rocks. So this is part of the country rock that was melted during this impact. There's low velocities at the top of the peak ring here that we think is an impact breccia sitting on top of the peak ring, and we'd like to try to understand that. So FWI is beginning to let us see details into this impact crater, and of course we can do this on the Earth. We can't do this on the Moon or on Mars or anywhere. We have to do it. We have to do this on the Earth, and we can also drill into these things. So there is a drilling proposal which goes forward in the drilling will start, I think, in about March next year, and Joe will be on that drilling rig for about 2 months, drilling basically through into this peak ring. Actually, I should say, Hamish, you did your PhD on this, didn't you? So Hamish did his PhD on this on an earlier version of this the seismic surveys across Cheeks. So and there's lots of things that we'd like to understand from this. So that's one sort of application. Second application I'm going to show you is a synthetic test across the Brazilian margin. We hope one day that somebody will shoot the data. So this is a purely synthetic test. The sort of acquisition geometry we've got is shown here. It's fairly sparse. It's a model that's, for the Brazilian one, it's about 15 kilometers in the cross-line direction. It's actually a bit longer than 100 kilometers in the inline direction, and it's got fairly sparse OBSs. I think we used about 300 to 400 ocean bottom nodes in the Brazilian case, and fairly tight air guns in this synthetic study. So this shows somebody's interpretation of what the Brazilian margin might look like based on a variety of things, based on data from Brazil and also based on data from the conjugate margin. So it's a cartoon. Not all the details will be correct, but many of the details will be broadly correct. And we'd like to try and understand some of this deeper structure. Where is is there a clear break between continent and ocean, and where, if so, where is it? And if there isn't, what is this intermediate region that might be quite complicated, might be intruded, and might be a mix of continent-like and ocean-like material? And what else is there? May be bits of mantle caught up in this region. All sorts of things might be going on. So we can look at that with FWI. We made a model. So this is a three-dimensional, fairly simple geometric model of what the margin might look like. The upper part is basically based on conventional seismics, conventional reflection seismics. The deeper part is based partly on imagination and partly on that reconstruction of what the margin might look like. And there are various features in there that we'd like to try to see if we can image. There's the moho. There is a layering in the lower crust. There's an ocean-continent boundary. There is some deep structure in the bottom of the sedimentary basins, various other things. So if we generate synthetics on that data and try and invert it, then we get a picture that looks something like this. So this was our starting model. So we assume that conventional seismics can really tell us what's happening in the top few kilometers of this quite well, but what we're trying to do here is invert what happens at depth. And you can see we do recover a lot of that detail. We can see this margin here. We can see this deep sedimentary structure below the salt. We can see the layering in the lower crust. We can see the moho, and so on. So if we shoot a reasonably well-constructed seismic experiment, large-scale experiment across the Brazilian margin with long offsets, with offsets up to 100 kilometers, then into ocean bottom nodes, then basically we would be able to recover the deep structure in that section. So the next one I was going to look at was field data across an oceanic spreading center. So this is not a synthetic study. This is a study of real data. We don't really know what oceanic accretion would look like. So this is right under a mid-ocean ridge where we're building brand new ocean. There are essentially three models, or I guess two models really, this one and this one. These are end models, and then this was a hybrid between the two. And the key difference is we know that you intrude sills, gabbros essentially, relatively shallow up here, relatively shallow in the crust, so there's melting at depth. That comes up, intrudes at this sort of depth. In this model, the idea is that another intrusion comes in, it forms above that and pushes this one down. Another one comes in, forms above that and pushes this one down. So the flow is basically down and out. So everything's intruded at this level and pushes things down from above. In this picture, the idea is things that intrude at all levels. So we do get intrusion at the top, but we get intrusions at all levels, and things basically don't move down; they just move sideways. And so the temporal history in here is completely different to this one. And this one's a sort of hybrid. This has some intrusion into the interior, but still a lot of intrusion at the top. So there is downward flow and outward flow. So what you see, you see some of this in outcrop and some of this in drilling. So it's possible to abduct this onto the continent so you can go and see it in outcrop. But it's okay. So there's melting down here. So you're pulling two plates apart. You get uplift of the mantle. The mantle's hot, so it melts through decompression. The melts flow upwards quite rapidly. They're basalts, so they flow up, or they're basaltic. They flow up. They pond at their sort of equilibrium density level. So there's liquid material in here which starts to freeze. Then you generate some more material. Where does that go? Its gravitational position now is above the stuff that's cooled, so it wants to intrude above the old, above basically the old sills and dikes, and wants to basically push them down deeper into the crust. So this is sort of a physicist's simple model, but there's good geological and geochemical evidence that perhaps it looks a bit more like this, so that things don't actually get to their proper equilibrium level for various more complicated reasons. So people are trying to understand exactly what this looks like. So I'll go through this quite quickly. Seismic survey's been run over one of these mid-ocean ridges, and you can see the lines here are shot lines. So those are where the air guns were shot. The dots on here are all ocean bottom recorders. So you can see this is a very much sparser experiment than you would have in a typical petroleum prospect. So we've only got a few tens of ocean bottom recorders, and we've perhaps got 20 or 30 shot lines, so the shooting is dense along the lines, but it's very sparse across the lines. And you can see the numbers here. Our ocean bottom nodes are about 5 kilometers apart in both directions, and the shot lines are almost half a kilometer apart. So very sparse data set to try and carry out 3D FWI on. The travel time tomography, this shows two different travel time tomography models, two horizontal slices through those at different depths, and this feature through the middle, and this feature through the middle. Unfortunately, the color scales are quite different. This is a low velocity feature. This is also a low velocity feature. That sits underneath the plate boundary where the plates are being pulled apart. So this is where things are anomalously hot, and possibly also where there is liquid, where there is molten rocks sitting through the middle. So those are travel time anomalies. There's quite strong anisotropy in the ocean crust, but unlike anisotropy in sedimentary basins, the axis is not normally vertical. The axis is typically horizontal because the anisotropy is entirely controlled by fractures. And you can see this is the orientation of the fractures. So the anisotropy axis is horizontal, and typically it's perpendicular or approximately perpendicular to the ridge axis. And there's quite large anisotropy in here. So the anisotropy's up to, 16% is the darkest color. So in here, the anisotropy is often more than 15%, but with a horizontal symmetry axis, not a vertical symmetry axis. This is all travel time tomography. So the orientations and the size of the anisotropy is all from travel times. That's correct, yeah, with an assumed model, yes. So you do allow the axes to swing round, but you don't allow them to move away from the horizontal. So we can do FWI on these data. It's very difficult because it's so sparse. So this shows the travel time tomography. This shows the same sections run through FWI. You can see the resolution increases, but not nearly by the same amount that it would in a petroleum data set, and that's simply because the data itself is so sparse. We have very little data to drive the inversion. And perhaps the most critical feature, the mid-ocean ridge is here. It's it's this topography here with a small valley in the middle. This topography here, that's exactly where the ridge is. In this section here, there is an off-axis volcanic center here. So normally, all the magma at the surface will come out right on the ridge, will come out here. But for this particular section, there's an off-axis volcanic center there, so there is volcanic material spilling out onto the seabed at this high. This is this high is basically a small volcano, and you don't really see much. I guess you see a bit of asymmetry in the travel time tomography, but in the FWI you see very clearly that the low velocities are offset and seem to be dipping, and you can get a strong indication that the melt is moving in this direction. It's not moving straight up, but it's moving anomalously, and ends up more or less where it's supposed to underneath this off-axis volcano. So although the resolution is rather poor, we are getting evidence that we have something real in these velocity models, and we are seeing something in this that we don't see in the travel times. They're about 5 kilometers. So this distance from here to here is about 5 kilometers. So we have to do all sorts of extra things. We have to regularize really quite carefully and do a whole variety of things to make this work. But I think this data set is just about on the verge of not working. This is about the most sparse, the most difficult than you could manage. And of course, the aspiration is to do these experiments with a lot more sources, and especially a lot more receivers. So I think that's probably, of these sorts of sparse academic targets, that's probably about the most mature experiment. A couple of others that are going to happen soon. We're all going to Santorini, which is a volcanic island in the Eastern Mediterranean. We're going there in a couple of months' time to do a 3D FWI experiment. So Santorini looks like this. So this is a Santorini island. It's a great big caldera. You can see, well, partly you can see these are all the tourist hotels, and then there's a drop of about 300 or 400 meters down into the to the sea surface. The caldera goes about another 300 or 400 meters deeper down. So this cliff is about 600 or 700 meters high, dropping down into the caldera. So this caldera explosion was the biggest volcanic explosion that's occurred on the planet in the last few thousand years. It was the caldera explosion that wiped out the Minoan civilization. So the Minoan civilization was an early Greek civilization on Crete. If you know the legend of the Minotaur, that was where the Minotaur lived. So this explosion basically wiped out that civilization, and it generated a huge tsunami. The tsunami from this explosion was at least 250 meters high. So that's a much larger than any modern tsunami that people have seen in recent history. And this is probably the largest explosion that modern mankind has ever heard. There's certainly been nothing in the last 10,000 years that was as large an explosion as that. And the volcano is still active. It's still building up. This is a volcanic eruption in the middle. There's a little island in there. That's the volcano gradually building up. There is quite a large eruptible volume of magma sitting beneath this thing, and it will erupt again in due course with a huge caldera explosion. It will massively disrupt Europe. It will massively disrupt the Middle East and North Africa, and it will be a very, very major hazard for the Eastern Mediterranean. So clearly, we'd like to understand that better. So we're doing a seismic experiment over this thing. So here's the island of Santorini. So these are the shot lines. So even the dotted ones, all of these will be shot. We've actually got some more money, so we have some more equipment. But the yellow dots are basically ocean bottom seismometers. There'll be equipment on land here. We now have money to put equipment on this island and on a couple of little islands in here. So that's what the experiment will look like, and we're trying to examine these sorts of models. So I won't go at all through the details of this model, but here's the volcano at the top. Here's the base of the crust. This is roughly to scale. There's different chemistry and different processes happening in this system, and there is quite a large eruptible volume of magma collecting up here at a depth of about 3 to 4 kilometers. And when that's erupted, if that's erupted rapidly and there's a large volume of it, that's why you get these very large caldera collapse events. So we'd like to understand the plumbing of that. We'd like to understand the volumes, the amount of melt, the amount of volatiles. So we want to get physical properties basically through this volume. So that's going ahead soon. That's an experiment that was bespoke for 3D FWI, but still not really dense enough. And then the final one that I'll talk about is the Hikarangi subduction zone, and I've nearly run out of time, so I'll rush through this quickly. So subduction zones, they move, they subduct, and they can do that in 3 ways. They can do that aseismically, which means they move just semi-continuously and by creeping, by solid state creep, and there's really no earthquake events on them at all. They can move with these very large megathrust earthquakes, so the ones that destroy cities and kill large numbers of people and generate very large tsunamis. So you get very large megathrust earthquakes on these things. But there's also an intermediate version of earthquake where you get slow slip events. So the subduction zone is locked, but then it moves, but it doesn't move in a catastrophic large earthquake. It moves and slips quite large distances, but over several months. And then it can lock again for 10 years, and then it can slip again over several months. So we call these things slow slip events, and they're basically revealed by GPS measurements and so forth. And so we'd like to know, why do some parts of some subduction zones move like this, and some like this, and some like this? And if it's busy moving like this, is this possible? Or if it's moving like this, does that really mean that's not possible and that's a safe subduction zone? So we'd like to understand the whole system. It's thought most likely that the differences between these 3 are due to fluids and the properties of fluids in the fault zone between the overriding plate and the underriding plate, and of course seismic properties, VP-VS ratio, attenuation, perhaps the anisotropic parameters are all sensitive to the fluids, and this is a highly overpressured region deep in the earth. So seismics ought to be able to tell us something about that. So this is the Hikarangi subduction zone off New Zealand. So this is the plate going down, basically, on a seismic image. This is the overriding plate. This is about 6 kilometers or so. So this is drillable, and there is proposals to drill shallow holes here, and then there's a proposal, actually a funded proposal, to drill right through the subduction zone, which will go forward in about 2 years' time, to drill through into this region and look what that boundary looks like. This is a piece that is moving with slow slip. So this is neither continuous slip nor these megathrusts. It's moving with slow slip. And the question here is that fine? Will it continue slow slip forever, or might it lock, and does it have the potential to generate a megathrust, very dangerous megathrust? So there's drilling going on there. To support the drilling, we're doing a 3D seismic experiment. So there'll be conventional 3D seismic offshore. So here's New Zealand. The Pacific plate here is basically subducting down to the west or to the northwest beneath New Zealand. The contours are contours on the subduction zone as it goes down. The crosses are the drill sites, and there's one offline here. So we'll do a conventional 3D survey in that box. We will have about 2,000 OBSs sitting in that box. We'll have about 200 OBSs. 200 OBSs in that box. We'll have about 200 land seismometers sitting in this region, and a conventional, fairly dense 3D towed streamer survey in the region there. We've done some modeling and inversion to see what we might recover, and this just shows a summary of that. So this plane in grey here sits on the subducting surface, and we've made a model based on travel time tomography, and then put a checkerboard pattern on that interface, and then used our experiment, used where the OBSs and so forth are going to be, to to see if we can recover the checkerboard. And you can see we do recover the checkerboard along that surface. These numbers are depths. So this is 6 kilometers, actually 6 kilometers below the seabed, and then this is 7 kilometers below the seabed. And we can recover things down to about 7 kilometers, and then we start to run out of resolution, partly because now we've moved under the land surface and we've got no shots in this region. But in the region where we've got good data coverage, we should be able to recover certainly P-wave velocity, and we hope in due course other physical properties along the subduction zone. So these are the sorts of targets we want to hit and the sorts of experiments that are being done and that we would like to do better in the future. So that brings me to the last question. So how might Brazil contribute to this? And I think there is something absolutely unique and very special that Brazil could do if it chose to, and it's this. So you have this marvelous 1% levy. You have a lot of petroleum that's produced. That levy is spent in R&D. So what could you do with that? So one thing you could do with that is spend a piece of that to fund a state-of-the-art seismic vessel for 3D scientific seismic acquisition. And why might you do that? You might do that because currently there is no other country in the world that is able to do that. So the US has a vessel which is definitely not state-of-the-art. They bought it from Western some 10 years ago. It has 4 cables. They are about to get rid of it because they can't really afford to run it. Europe doesn't have one. Japan sort of has one, but has not been very successful at using it. No one else has one in the world. So if Brazil was able to spend a piece of its levy to get a state-of-the-art seismic vessel, a genuine, modern 3D seismic vessel, dedicated to scientific acquisition around the world, your country would immediately lead the world in this whole endeavor. There is nobody else that is going to do that. It's also a wonderful time to do it. Well, wonderful if you're on one side of the equation, not if you're on the other. So seismic contractors are having a hard time. They are getting rid of their boats. They are getting rid of their crews. It's a cheap time to buy a boat. It's a cheap time to find people with expertise and equipment available in this field. And I think if you are able to do this, this would place Brazil in a world-leading position in geoscience. All the best groups in the world will want to come here. They will want to collaborate. They will want you to take your ship to look at their problem, whether it's in New Zealand, whether it's in Brazil, whether it's wherever it is, where there are interesting targets. And I think it's absolutely no exaggeration that if you did this, that Brazilian geoscience would overtake what we're currently able to do in the US, in Europe, in Japan, basically everywhere. There is no other country whose government is willing to put this sort of money to fund a genuine 3D seismic vessel, and you could do it through the levy. It doesn't need all the levy. It needs perhaps 20% of the levy dedicated to this over 10 years. You could absolutely look at every interesting target in the world and do something really, really dramatic. So I'd like to recommend that to you. I'd like you to take this and recommend it to the whole country and get the message to the people that really need to know, and perhaps change the way the levy's operated and do something really very, very dramatic for Brazilian geoscience. So that's the proposal. So if I can summarize, there are lots and lots of questions in the earth sciences that we can only address with knowing something about subsurface physical properties. 3D FWI has the capability very often to tell us that, and it makes these sort of wonderful images in a petroleum context. And if Brazil chose to, you could really be the world leader in this whole field, and do it in such a way that all the best academic and technical groups, scientists, engineers, and so on, would all involve themselves in doing this, because you had this Brazilian ship, which simply no one else had the capability to do. So I'll leave it there. Thanks.